Today we're going to look at section 7.5, Properties of Logarithms. Our objective is to be able to switch between exponential and logarithmic form, to be able to use the chains of base formula to evaluate logs on the calculator, and to be able to expand and condense using log properties. So why do we use logs? So what a log is, it's a way for us to help solve exponential problems using our calculator. So if we look at the first example, 2 to the x equals 8. That one's not too difficult because we're asking 2 to what power is 8? Well, we know 2 times 2 times 2 is 8, so x equals 3. Likewise, if we have 2 to the x equals 16, we know that 2 times itself 4 times is 16, so it's x equals 4. But what if we get a problem 2 to the x equals 10? This is much more difficult. We could probably guess and say, well, since 10 is between 8 and 16, x is between 3 and 4, but, where is it exactly? And that's why we use logs. We use it to help us solve problems when we don't know the exponent. So now let's go through a couple of the things. Let's figure out first, how do we put it into log form? Well, if we have exponential form, a to the y power equals x, that converts to log base a of x equals y, and that's how we say it, log base a of x. So how can we move from one to the other? If we look at this power, it has a base of a. If we look at the log, it has a base of a. Now, it's not exactly like this, but if I cross off the log and don't look at that, it looks like a to the x equals y. This is a to the y equals x. So if you can remember, we're just going to switch the position of x and y when we put a log up. Maybe it makes it a little easier. Even though this is not an exponent, because this is a base, it might help you in switching between one form and the next. So let's actually go through a few. If I give you exponential form of 3 to the x equals 243, it's going to be log base 3 of 243 equals x. So again, if you cover up the log, it looks like this, except for the exponent and the answer is switched. How do we work backwards? Log base x of 81 equals 4. Well, you keep the base the same, x, and now it's going to be to the 4th power equals 81. Again, let's go backwards. X to the 6 equals 12 is going to be log base x of 12 equals 6. And our last example, and we can make this look as crazy as possible as we want. The thing we need to know in the future when we're solving is the base and the of value always have to be positive when dealing with logs. But in this case, since we're not solving right now, we don't have to worry about it. But other than that, I can pretty much write whatever I want here. So if I switch back, the base is 2, of my exponent, my power is 2 to the 5th equals x plus 2. And that's how you go back and forth between the forms. So now we're going to have to use our calculator. Now, if you have your calculator up, log is found right here, right next to the 7. So how do we actually use our calculator to use logs? If you actually take your calculator out, the log button is found right next to the 7. It says LOG, and it stands for logarithm. Okay, and that's the button we're going to hit. When we hit the button, when we actually hit log, turn this on, I can type in numbers. However, it doesn't give us the option to put that little base number. It's because the calculator has something what's called the common logarithmic function. It has an imaginary 10 here. So most of our problems has a base other than 10. So let me just show you how this works. If I put in log of 100, I should get an answer of 2, because what this is asking is 10, our imaginary 10, to what power is 100? Well, it's 2. If I typed in log of 20, or let's say log of 1000, it's asking 10 to what power is 1000? That's 3, but it's only in powers of 10 because the base is 10. So we have to use something called the change of base formula. So I have log of any number of x, so a and x can be any number. How we type into our calculator is log of x divided by log of a. So we take log of our of value divided by log of our base. So let's go through a couple of examples here. The first one says log base 7 of 120. So how do I do that? Well, in my calculator, I'm going to type in log of 120, close the parentheses. That's the most important thing. Most students forget to close it and they get all wrong answers. Divided by log of my base value, which happens to be 7. That's how you would type it in your calculator, and we get an answer. And for this one, we want you to round to 3 decimal places. So if I have log of 120 divided by log of 7, I get approximately 2.460. What am I going to do the next one? Well, again, this is not a 10, so I need to do log of 15 divided by log of 12. And if I type that into my calculator, I'm going to get to 3 decimal places, 1.090. So again, let me show you that. Log 15, make sure you close the parentheses, divided by log of 12. The last parenthesis isn't as important, but the first one is. And again, if I go to 3 decimal places, okay, this 7 is going to make this a 0, which makes this a 9. My last example says log of 85. Now there's no base. If they don't write a base, they're implying that it's a 10. So when I go to my calculator, I don't need to do any change of base formula because it has the same base as my calculator. All I would do is type in 85, and that's where I get my final answer, approximately 1.929. And that's how you use your calculator when we're dealing with change of base. So how are we going to actually solve problems? So these are the same 4 examples that we had at the beginning when we changed from one form to the other. Some of these you might be able to just do in your head if the number comes out to be an integer, something nice. But some of them are going to be a little bit more difficult. So anytime you have something like this, you might think, well, how do I know which form to change it to? Well, 3 to the x. I can't type that in my calculator. So if you don't know this off the top of your head, what we'd want to do is change it to log form. Log base 3 of 243 equals x. Now the x is isolated. These are all numbers, so I can just type this in my calculator. Log of 243 divided by log of 3, and if I do that, I get an answer of x equals 5. I can always substitute it back in to make sure it's correct. 3 to the 5th is 243. What if it's already in log form? Well, it'd be nice to type this into my calculator. However, I can't type log of x because the calculator doesn't know what x is. So when it's in log form, sometimes it's important to change it back to exponential form. This would be x to the 4th equals 81. We've already done problems like this. If I want to get x by itself, I have to take the 4th root of both sides. So I would have to do that. But if you notice here, I just say the answer is x equals 3. And we should know from our last chapter, when we take the even root of both sides, we get a plus or minus. The reason why this is positive is because when you're dealing with logs, and my original problem was a log problem, the base number and the of value always have to be positive. So even though normally I would get a plus or minus 3, if I check back in my original, if I put a negative 3 in here, that wouldn't work, so 3 is my only answer. In my third example, x is 6 equals 12, I don't want to change this to log form because if I do, I'd get log base x, and in our previous example we saw that having a base x isn't good. So how would we solve this? Well, I would take the even root of both sides. And when I take the even root of both sides, I know I need to have a plus or minus. So if I actually simplify that, x equals plus or minus root 12. Now here I kept the plus or minus because if I substitute back into my original problem, which was an exponential form, a root 12 to the 6th power is 12. A negative root 12 to the 6th power is also 12. So this is why you have to be really conscious of conscientious about what kind of problem you're started out with. In our last example, log base 2 of x plus 2 equals 5. Again, I can't type this into my calculator the way it is. What I need to do is change it to exponential form. 2 to the 5th equals x plus 2. Well, this I can just solve easily. 2 to the 5th is 32. Subtract 2 from both sides, and I get x equals 30. And again, if I substitute 30 into my original, this is 32, which is positive, so I don't have any problems. So we're going to go through 3 rules of expanding and condensing. So there's 3 of them. 1, 2, 3. The first one deals with when you add 2 logs. Now the important thing to know with all these rules is the base number has to be the same to do any of these rules. And in our examples they will always be the same so we can actually do the problems. So log base a of m plus log base a of n, we can combine that, condense it to make it one log base a of m times n. If I started with this, if I'm multiplying values, I can expand it to 2 separate logs. My second rule says, what if I'm subtracting the two logs? Well, then it says we divide the two values. And the third rule says, if you have a number times the log, that number could be raised up as an exponent to whatever value you have here. So we're going to go through some examples. These first two examples deal with rule number 1. So I'm going to kind of go through the steps here. I'm adding two logs with the same base, so I can condense it to one single log. When we say condense, we want everything written in one log. So this would be log base 2, and the rule says that we're going to take 7 times 4, so I'm going to get log base 2 of 28, and that's it condensed. What if I already have something multiplied together? Well, then I'm going to ask you to expand it. I am multiplying the 6 times the x times the y. So the rule is very generic. It always shows you two things, but we now have three things multiplied together. That doesn't change anything. This would be log base 5 of 6 plus log base 5 of x plus log base 5 of y. Anything multiplied together we separate with a plus. Rule number 2 deals with minus, or subtracting our two logs. So if I condense this to one single log, I'm going to get log base 4. Since I'm subtracting, I'm going to divide my two values. So I'm going to get x divided by 12. I can't simplify that, so that's my final answer. If they give you a problem that already has division, we can expand it by taking log base 7 of the numerator minus log base 7 of the denominator. My third rule deals with exponents. So if I have 3 times log base x of 5, to condense it, to make it where we start with the word log, I'm going to get log base x of 5 cubed, or log base x of 125. If I expand and I have an exponent, this exponent ends up coming out front. So it's going to be 4 times log base 2 of b. Now we have problems that are a little bit harder. I'm going to give you a much longer problem on the test, something that looks like this, not like the first couple of examples. What I want you to do is put all the rules together. I have multiple logs here, so my goal is to condense this, which I would tell you on a test, to condense into one single log. So how do you know which rule to start with? You always want to start with rule 3, the exponent. So the only lead coefficient I have is this 4. So what I'm going to do is rewrite this as log base 3. Now 2x is with this log, so I have to make sure the 4 goes to an exponent for both of those. So I'm going to use parentheses to show that. Log base 3 of y minus log base 3 of z. Don't worry about taking lots of steps to do this. Sometimes students go way too fast, try to do too much, and they miss something. So I'm going to take it a little bit slower on the notes. Now I'm going to simplify this. 2x to the 4th, well 2 to the 4th is 16, x to the 4th is x to the 4th. Plus, and I'm just going to rewrite everything else. Log base 3 of y minus log base 3 of z. Now I have just an equation with addition and subtraction. When that's all that's left, PEMDAS says we move left to right. So the first thing I see is an addition sign, which means to condense that, I'm going to multiply these together. So 16x to the 4th times y is just 16x to the 4th y. And then I'm going to rewrite what's left, minus log base 3 of z. Now I'm subtracting two logs, which means I take the first as my numerator, the second as my denominator. So I get log base 3 of 16x to the 4th y all over z. I've gotten it down to one single log, so that's when I know I'm finished. In our last example, I want you to put all the rules together to now expand our log to multiple logs. So how do you know how many logs you should have when you're done? Well, what I do is I count how many terms I have. So if I look, I have a 3 times I have an x, a y, and a z. So that's 4 terms. So that means I'm going to have 4 logs when I'm done. And for us, we always want to start with the division first. So I'm going to separate that into a log of the numerator, so 3xy squared, minus log base 5 of the denominator. That's the first thing you want to do. I always like to simplify any parentheses I have or exponents. So this is 3 times x squared y squared. I find it makes it a lot easier in the end. Minus log base 5 of z. Now you want to deal with any terms you're multiplying together. This one's just by itself, so we don't have to deal with that, but this is 3 times x squared times y squared. So I'm going to write that as log base 5 of 3 plus log base 5 of x squared plus log base 5 of y squared minus log base 5 of z. Okay? So now what do I have to do? Well, this is okay. Here, these two I have exponents. So I can leave log base 5 of 3 by itself. But I'm going to pull that 2 out front. So we get 2 times log base 5 of x plus 2 log base 5 of y minus log base 5 of z. And that would be my final answer. Every single log is log with the base, and I have just a single variable here, either a variable or a number. All of my exponents are written out front. You can always do a check, try to condense this, and see if you get back to the original. I hope you feel a little bit better about logarithms, being able to switch between exponential and logarithmic form, being able to use the change of base formula in your calculator to evaluate and solve, and to be able to expand and condense using log properties.